Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll continue learning about linear models, and we'll talk about Lasso, LassoCV, and MultiTaskLasso. So Lasso is based on L1 regularization, and we'll look at the intuition of that, and then we'll look at an example of computerized tomography where L1 regularization is used. And finally, we'll look at the code snippet. And then in the following video, we'll look at the actual implementation in Python. So far, we have seen that ridge regression uses the L2 regularization where the parameters can go close to zero, but they do not go completely to zero. They cannot zero out or eliminate parameters. However, in case of Lasso, the advantage is that with L1 regularization, the parameters can go to zero, and thus some of the parameters could be completely eliminated from the model. And here is the objective function for the lasso regression, which is minimized for W, and this is similar to what we have seen before. Here there is this particular part, which is we are taking the mean, we are dividing by 2 into number of samples, and the L1 norm that is added here, that's the regularization term for L1 regularization shown here in blue. It is just simple absolute summation. So all the values for the parameters, absolute values for the parameters are added, and that term is added to this particular objective function. In addition, the alpha regularization parameter is the same as it was before. Now, you've seen this similar slide for L2 regularization. The concept is similar in case of L1 regularization. The difference being that in this case, the instead of the circle, which was for L1 regularization, here we have a rotated square that defines the boundaries for the parameters. In this case, W1 and W2. And the advantage of having this square shape is that it has corners where the parameters can get to a value of zero rather than going to a value close to zero. And as we can see here on the red dot, the value of the parameter w1 would be zero because it's directly on the y-axis, and thus we can see here on the right hand side the intuition that that parameter then now can be completely eliminated. And thus in addition to uh, regular adding in addition to moving away from overfitting, this parameter also this type of regularization also helps in making the model more sparse, so a less number of features can be used. Here is a concrete example where we have these five parameters, and let's imagine that we are trying to predict the forest cover, that's the percentage of trees or forest land. And as the some of the parameters, the first three, rainfall, temperature, and altitude, are definitely important for predicting this. However, the number of cats and the cost of coffee is definitely not relevant. So what when we use the lasso regression, what we can get in the output is that some of the parameters such as W4 and W5 in this case would have the coefficient. So these coefficients would have the value 0. I'm using the word coefficient and parameter interchangeably here. So essentially, these two would have the coefficient value of 0, and therefore, in this equation, when we substitute these values for W1, all the W's, the the X features X4 and X5, that is the number of cats and cost of coffee, would be multiplied by 0, and thus they will be completely eliminated from this prediction model. And therefore in the final model would consider only the important features that are just rainfall, temperature, and altitude. Here is another example for lasso regression that's used in computer tomography. And on the left hand side, we see an object in which is to be scanned using the CT scan. The CT scan, you probably already know, is computed tomography. And what tomography means is taking slices or sections of a particular object by methods using waves such as X-rays that can penetrate through the material of that object. And in the middle, we see one such section where the scanner is moving in this direction, and this is the data that is collected as the scanner moves through. And for computer the CT scan, several such scans are performed from different directions, and then those are projected uh, to reconstruct the image. And that's where the lasso regression is really helpful. So this is an example which is adapted from the code here by Emmanuel of on Scikit-learn site. That is the link. So here, if this is the original image, the uh, the projected image can then be uh, uh, passed through regularization. And here, this is based on the L2 regularization, where we see that there are still several artifacts or noise around the actual image that's right here in the center. And the reason is because out of 2500 features, none of them go to zero. All the 25 coefficients have the non-zero values. So as we saw in the previous equation, none of these goes. So all the parameters have at least some value. So even the noise in these images would continue to stay in that particular image as it is reconstructed. However, when we use the L1 regularization, we see a clear image where only the object is visible. And this is possible because out of the 2500 features, only 256 features are non-zero, and about 2200 features have been zeroed out, and so they are eliminated. And those features are likely the noise that's around the actual object. And so that's that type of zeroing out the features in this case helps to get a clearer CT scan image. Now, moving on to Lasso CV, it is similar to Rich CV that I've seen, where the cross validation is built into the Lasso, and this does exactly that. Now, another additional method here we have is a MultiTaskLasso. So the objective function is for Lasso is on the top, as we see here. We have this term for regularization. Now, in MultiTaskLasso, what it can do is, instead of just one regression output, so you typically would have just one column of numbers for output for regression. However, in the multitask lasso can handle more than one output columns. So, therefore, the W term here is capital, and Y is also capital because it's a matrix that is output. And hence, we have the norms that are changed. So instead of L2 norm here is a Frobenius norm. It works the same way as the L2 norm, except because this is applied to a matrix, it is a Frobenius norm. And here there is additional L2 and L1 norms instead of just L1 norm as we had above. So the Frobenius norm, as we've seen, it is the same as the L2 norm, where we are taking the squares and sum of squares and then taking the square root of that. And here this is a sequence of L2 and then some of those values right here where we have uh, A, which is kind of example matrix. So instead of A here, it will be W when this is calculated. And the code snippet is similar to what we have been seeing in the scikit-learn implementations. We import the linear model, have the train test data, and then we initialize the variable reg, and by calling linear underscore model dot lasso, again we can tune the value of alpha. uh, and alpha, if you remember, it helps um, constrain the values of the parameter w. So uh, you can increase it or decrease it and then see which works, which value of alpha gives the best level of mean squared error. And once that is initialized, we fit it to the train data, x train, y train, and then finally use that to predict on the test data. And if it's a validation set, then there will be prediction on the validation, then we'll loop through the train set again, and once the model is finally ready, then that can be used to predict on the test set. So that was it for this video. I hope in this video you got an intuition about what is lasso and how L1 norm works, as well as how the multitask lasso works. As and from the perspective of applications, I hope you found the example for the rainfall or for the prediction of forest cover kind of intuitive to see how zeroing helps, as well as the example for CT scan images, how zeroing helps. In the following video, we'll look at the implementation in Python. Until then, please like, share, and subscribe. I hope to see you all in the next video. Thank you.